everybody. Thank you for joining Cisco ACI PBR session. My name is Minako Higuchi. I'm a technical marketing engineer, part of data center switching group. That is a business unit producing Nexus 9K and ACI. I've been working on ACI almost from beginning, especially focusing on policy, forwarding, and service integration. That is exactly the topic today. I do apologize, I cannot take your questions during while I'm presenting. So if you have a question, please join WebEx space. You can find it in the Cisco event app. I promise I will take a look at your questions after my session. Session objectives. After this session, I hope everybody understands what is the ACI PBR use cases, how it works, and what's the typical design considerations. And then I'm also talking about multi-site service integration design by using PBR, including how to configure it. Initial assumption is you already know what is ACI. This is level 3 session. So I'm not going to talk about the basics, such as what is bridge domain, VRF, EPG, ESG, and so on. In my presentation, I mainly use ESG, endpoint security group, in the PowerPoint illustration a lot. But PBR feature perspective, it doesn't matter whether it's EPG, ESG, or USEG EPG. This is the agenda. I'm going to talk about the PBR use cases first, and then how it works, including forwarding and zoning rules. Then I'm going to cover what's the typical design considerations by walking through commonly asked questions. Then I'm going to cover multi-location data center design and consideration. The first topic is PBR use cases. Where can we use PBR? To understand this question, the most important factor is PBR redirect is one of the contract actions. I believe everybody knows contract permit because this is almost mandatory component in ACI. We have other actions such as deny, redirect, and copy, which means wherever contracts can be applied, you can use PBR. Contract is based on source, destination, and filter. Let's take a look at a couple of examples. Let's say you have multiple EPGs, external EPGs, having a contract between them. You can permit traffic, which means you can also redirect the traffic. Even between EPGs or ESGs in the same bridge domain subnet, we can redirect traffic to the firewall. This intra-subnet firewall inspection might be pretty difficult in the traditional network. But thanks to contract in ACI, we can easily redirect the traffic to firewall. Even within EPG or ESG, we have intra-EPG or intra-ESG contract, which means even between endpoints in the same security group, we can inspect the traffic by firewall. This is pretty flexible. We can think of other use cases. As I mentioned, contract is based on source, destination, and filter. This example is based on filter-based redirection. So let's say you have TCP traffic to be redirected by firewall, inspected by firewall, so that you can just permit other traffic going on if you don't care stateful inspection that much for that traffic. In that case, you can create two subjects under the contract between EPGs. First one is TCP redirect. The second is permit IP, so that you can take advantage of precious resource of firewall, because if you redirect everything to firewall, it's going to exhaust firewall, potentially. The next example is source-based redirection. Let's say you have shared external EPG where you have multiple internal EPGs or ESG going to talk to external network. So destination is the same, but based on source, you want to insert a different firewall. Then you can create a contract 1 between ESG1 and the external EPG. The action is redirect traffic to firewall 1. You can create another contract to redirect traffic to firewall 2. So this is a source-based PBR use case. I've been using firewall, for example. Most likely for firewall, you are going to use PBR for both incoming and return traffic. How about load balancer? For load balancer, it's most likely you are not going to enable PBR for incoming traffic because client is going to send the traffic to the BIP owned by the load balancer. There's no need for redirection. That said, for return traffic, if source NAT was not enforced by the load balancer, you might need to get return traffic back to the load balancer. In that case, you can enable PBR for return direction only. The point here is that PBR can be applied for both directions or either one of them, depending on your use case. I hope this kind of gives you some basic idea of the use case of PBR. Then what's the mandatory requirement to use PBR? Two important requirements. First one is ACI must be layer 3, which means you must use BDSVI as the gateway of servers. The reason is that PBR is actually rewriting destination MAC to get traffic redirected, which means it's routing. So ACI must route traffic. If you have been using firewall as a gateway, you must migrate gateway from something to ACI fabric to use PBR. The second important factor is VRF must be enforced mode. As I mentioned, this is contract. Without having enforced mode, we cannot enforce policy. Then you might be wondering, what if I want to permit everything? Then you have two options. First option is with any. The second option is preferred group. I personally recommend with any, so let me double click on what with any is. With any is a logical object representing all of the EPGs, ESGs in the VRF. So basically everyone in the VRF. If you have some specific provider EPG that everyone needs to talk, instead of creating multiple contracts, you can just create one contract between VZNE and the specific provider EPG so that you can let everybody talk to the provider. You can use redirect so that you can enforce specific common traffic redirected to firewall by just using one contract. You can even do VZNE as the consumer and the provider. I would call it VZNE to VZNE contract. That basically permits all of the communication within the VRF. This is just one TCAM consumption. This is pretty useful. And if you want firewall enforcing all of the communication in the VRF, then you can enable redirect for VZNE to VZNE contract. If you have some security team who wants to manage everything on the firewall in terms of security, then you don't have to deal with complicated contract configuration. Instead, you can just use VZNE contract, redirect everything to the firewall. Since I briefly touched upon zoning rules, the next section, I'm going to double-click how it works. Let's start with zoning rule. Imagine you have a permit contract between one consumer and one provider. Each EPG ESG has unique identifier that is called class ID or PC tag. it's not going to be something you're going to allocate it, Epic going to allocate dynamically. If you have one bidirectional contract, we have a permit rule from 29 to 10934, and return traffic 10934 back to 29 should be permit. So if you have one bidirectional contract with one consumer and one provider, we're going to consume 2 TCAM consumption. Then if you apply service graph, PBR, firewall with 2 arms, internally we will update zoning rules like this. Let's take a look. For the service device interface, we also internally allocate service EPG class ID. Let's say 30 for the consumer side, 32 for the provider side. Then consumer to provider traffic, 29 to 10934, the action is redirect to the consumer side of firewall. Then firewall routes traffic and enforcing security policy. Then traffic comes back from 32, and then destination is still 10934. So 32 to 10934 is permit. And then the return traffic, 10934 to 29, this is also redirect action, but it's pointing to different PBR destination that is provider side of the firewall. After that, firewall sends traffic back by using consumer side of firewall. That's going to be 30 to 29. This is permitted. So it's automatically done. Usually you don't have to pay attention that too much. But imagine you need to manage this by using NXOS or some other switches manually. You need to think about ingress access list and egress access list, where device is connected and so on. But thanks to contract and service graph, it will be automatically updated. You might notice that 1 out of 4 zoning rules here have default filter. 14 filter in this example, let's say this is permit IP filter. We don't use that filter after the first redirection by default. The reason is that assumption is firewall already inspects traffic. So there's no point to have specific filter, because the specific filter will consume more TCAM resource. So we decided to use default filter after the first redirection. But for some use case, we need to keep original filter instead of default filter. This is the configuration option available at service graph template. But you might be wondering when we have to pay attention on this. Here's an example. Let's say you have UDP redirect rule between ESG1 and ESG2. This is completely fine. And then you have another contract. If it's TCP, after firewall, you want to redirect traffic again to the IPS or some other device. Then the first action, consumer to provider, this is the same, redirecting traffic to firewall 1. After that, 32 to 10934, if it's UDP, we want to permit. But if it's TCP, we want to redirect. To differentiate UDP and TCP, we need to keep original filters from contract. So if you have this sort of advanced use case, please keep in mind you might need to enable this option. Another important CLI command is to check the aliveness of a PBR destination. So in ACI, PBR, any leaf can potentially apply policy. But we don't let all of the leaf switch send keep alive to the PBR destination because it's going to be a mess. Imagine you have 20 or 30 leaf switches immediately sending IPS area traffic to one PBR destination. That's bad. So we decided to get service leaf node. The local service leaf node takes care of IPS area tracking. And then, based on the result, the service leaf is going to distribute that information to other switches in the fabric. Another important concept is health group. Health group has a special behavior, especially important for two-arm design. Let's say you have 11.1 and 12.1. If one of them is down, we should stop using the other side, otherwise traffic is going to be black hole. So the idea is if one of the members in the same health group is down, we're going to stop using all of the members in the same health group. Let me go back to zoning rule. So let's take a look at advanced use case, two-node service graph. First node is firewall. PBR is enabled for both directions. The second node is load balancer, where we enable PBR for return traffic only. Then the zoning rule will be like this. Let's take a look at step by step. So consumer originally send traffic to VIP instead of provider directory. Then what we need is 29 to 10937 redirect traffic to firewall. After that, 32 to 10937, we just need to permit. After that, 5481, load balancer to provider, finally, 10934, this is action is permit. Then the return traffic, since load balancer didn't perform source NAT, web is going to send traffic to client directory. So it's going to be 10934 back to 29. The action is redirect to load balancer. Then 10937 back to 29. We need to redirect to firewall. And then finally, 30 to 29, this is going to be permitted. So even if you have 3 node, 4 node, it's just concatenating these kind of rules. One important design consideration for load balancer. Typically, load balancer does some sort of keep alive to check the aliveness of web endpoint in this case. Then it's a communication between 5481 and 10934. But as you can see, we have 5481 to 10934 permit, but we don't have a permit rule for return direction. So by default, it's not added, but we have a way to add it. So by default, this is also to reduce TCAM consumption. We don't add bidirectional permit rule between service device and the consumer provider. But for some reason, if you want to permit the direct connect, you need to enable this option. This is available at the service graph template. Since I've been talking about zoning rules to determine what's the expected forwarding decision, so let's take a look at actual forwarding path. Let's say you have consumer 192.168.1.1 on the left, and then 2.1 provider is on the right. And then in between, you have firewall, 2-arm inserted. For illustration purpose, I just put everywhere under different leaf nodes, different bridge domains. But you can get everybody under the same leaf, or you can just use one bridge domain for consumer, provider, and firewall. So this is just an example. So let's say 1.1 consumer sends traffic to provider. If ingress leaf doesn't know the destination yet, source class ID can be resolved, but destination class ID, it's unknown. So there is no way to enforce policy. Then traffic is going to spine proxy, and then spine should be able to handle where 2.1 is located. So traffic is going to leaf 3. Because the source class ID information is in the VXLAN header, the egress leaf 3 can resolve both source and the destination class ID. Consumer to provider, the action is redirect. We already checked that in the zoning rule. At the same time, leaf 3 is going to run 1.1 under leaf 1. This is data plane IP learning. Then PBR kicks in. What we are actually doing is that rewriting destination MAC and segment ID. So we know what's the PBR destination IP and MAC, and what is the service BD. That is part of configuration. So we can redirect the traffic without changing source or destination IP. Then it's just breached. Traffic is going to firewall, consumer side. One important forwarding note. In this illustration, I put firewall and leafs and destination under the different leaf. Even if firewall is under leaf 3, because of this rewriting behavior, traffic is always going to spine proxy. So usually you don't have to pay attention on this, but when you are doing some troubleshooting and then taking a look at the hop by hop packet path, then you might need to know that it's always spine proxy. After that, firewall sends traffic back. Traffic is going to destination. Here, redirection doesn't happen again because source class is not consumer. Now source class is provider side of firewall, going to provider. The action is permit. Then traffic is going to the 2.1. Another important consideration is that leaf 3 is receiving traffic from 1.1 through leaf 1 tap, a leaf 2 tap, but it's actually under leaf 1, so we shouldn't learn 1.1 after PBR. So we automatically put disable data plane IP learning flag if it's coming from service EPG, where PBR is enabled. Then the return traffic from 2.1 back to 1.1, now that leaf 3, ingress leaf knows the destination, then policy can be applied on the ingress. Then rewriting destination MAC, this time it's going to be provider side of firewall. And then traffic is arriving on the firewall, routed, security is enforced, and then going to the destination. Here we don't redirect the traffic again because this is from firewall consumer to consumer. Again, we don't learn 2.1 from leaf 2 because this is after PBR. And then finally, traffic is coming back to 1.1 consumer. So this is end-to-end traffic behavior, including PBR. You might notice that ingress or egress leaf apply policy. This is depending on EPG to EPG configuration or external EPG to EPG configuration or inter-VRF configuration or not. So I'm not going to explain each one of the combination. If you want to understand more detail, please take a look at the contract guide. That said, you might be wondering how ingress-egress enforcement works. So let me give one example. We have a policy applied bit in VXLAN header to indicate whether policy was already applied or not. Intra-VRF, EPG to EPG contract, if ingress leaf knows the destination already, then ingress leaf applies policy. If it's denied, it's better to deny it as soon as possible, instead of waiting traffic is going to egress. Then policy applied bit is set to 1, so that leaf 2 receiving traffic, taking a look at the VXLAN header, or policy applied bit is 1, which means leaf 2 doesn't need to apply policy. So leaf 2 kind of ignoring policy enforcement. This is ingress enforcement. If ingress leaf doesn't know the destination, policy applied bit is set to 0, which means leaf 2 can identify, oh, I need to apply policy. So leaf 2 going to apply policy, that is egress enforcement. So depending on data plane IP learning status, you might see ingress or egress enforcement. Since we talk about zoning rule and filter-based action, I'm going to double-click how we can mix permit, deny, redirect action. In a nutshell, the more specific configuration will win. EPG contract wins over EPG to VZNE, that wins over VZNE to VZNE. So more specific rule will win. If you have same granularity of contract, then deny action is the strongest action. And L4 rule-wise, more specific rule will win. I hope this makes sense, but it's probably hard to digesting what it means. So let me give you 3 examples. If you have new VRF having multiple EPGs, but you don't know what traffic to be denied or permit or redirect, so maybe you can start with VZNE to VZNE permit contract, just one contract permit everything. And then it's going to be just one TCAM entry, 0 represent VZNE, everybody. So 0 to 0, permit IP. In this example, filter ID is 74. The action is permit. As a result, all of the inter-EPG communication in the VRF will be permitted. Then you want to inspect the TCP traffic by firewall. Then you can add another subject, redirect TCP, in addition to permit IP. Then you're going to have 0 to 0, 14, permit TCP filter, action is redirect. Then on the right side, you can see the priority of each entry. These 2 entries have same priority. That said, granular filter will win, which means TCP traffic between ESG1 to ESG2, what would be the action? Redirect, because TCP is more specific than IP. Then ESG1 to ESG2 UDP, it's not going to hit redirect TCP action, but it still hits permit IP action. So this is an example of granular filter will win. The third example is combination. Let's say you have VZNE to VZNE permit initially, and then you want to inspect all of the north-south traffic. Then you can use VZNE to external EPG contract with redirect. In addition to that, you want a specific east-west traffic to be redirected. Let's say redirect TCP between ESG1 and ESG2. Then here is a quiz for you. TCP traffic ESG1, ESG2. What's going to be the action? Redirect, because this is the most specific rule. ESG1 to external EPG3. This is also redirect, because it's going to hit any 2 specific contract. If you have ESG1 to ESG2 UDP traffic, it's still permitted because you have VZNE to VZNE permit. Hope this gives you an idea of how to combine these 3 different actions. So in a nutshell, specific to specific wins over specific to VZNE. That wins over VZNE to VZNE. So I'm not going to talk about too much detail, but you can see the zoning rules and then see the priorities. So smaller priority ID will win, actually. So hope this gives you an idea what's the use case, how it works, and so on. Then it's always the case that when you start designing it, you might hit a couple of typical design considerations. So I'm going to talk about typically asked questions. The first and the most common question is, 1 arm or 2 arm? Which is better? The answer is, it depends. We have pros and cons. 1 arm would be better if you want to simplify routing configuration on the firewall, because it's just one static route. One default route pointing ACI bridge domain subnet as a gateway. That's it. This is also a requirement for VZNE to VZNE or intra-subnet contract. That said, your security counterpart that might not like it, because in case of ASA, we use interface as a security level definition. Then 2ARM might be better, but you still need to manage routing tables accordingly. But you can set different security level based on interface. The next question is, can we reuse the same PBR destination multiple times? The answer is yes. I've been using one EPG consumer provider contract as an example, but you can put multiple consumer EPGs and multiple provider EPGs reusing the same PBR destination. Even contracts are different, you can point the same firewall destination. So you don't have to create a new firewall or new interface depending on new contracts. So you can reuse same firewall as much as possible, if that makes sense. But the two considerations, even though we can put multiple consumers and providers, imagine you have 100 EPGs and another 100 EPGs. Then the combination is going to be huge. So you can easily exhaust TCAM. Instead, if you have redirect for majority of traffic, I would recommend VZNing. The second consideration is, even though we can redirect traffic flexibly, firewall needs to take care of routing. So please keep in mind, firewall routing perspective, your design is making sense or not. Next, what sort of device can be PBR destinations? The answer is almost anything. Prior to 5.0, PBR destination must be layer 3 device, which means the device owns IP and MAC. Starting from 5.2, we support L1, L2 PBR, and you can mix different types in the same service chain. For example, you have inline IPS, L1 PBR, and then transparent firewall, L2 PBR. Then the last node is PBR for return traffic for load balancer, that is layer 3. So you can mix required service types in the same service chain. This is pretty flexible. The next question is, I already have a perimeter firewall inserted between north-south. I want to use the same firewall for east-west. Yes, you can do this. So let's say you have firewall connected as a L3 out router. Then north-south firewall is inserted based on routing. No need to take care of PBR. Then you want to reuse the same firewall for east-west PBR. That's possible. That's possible after 5.2. Prior to 5.2, PBR destination must be in a bridge domain instead of in L3 out. Starting from 5.2, you can use PBR destination connected through L3 out. Here is the configuration. Let's say you have a contract between two EPGs, east or west. Action is redirect, and then PBR destination is in an L3 out. And then L3 out EPG to internal EPG, you can just create another contract with permit so that firewall is just inserted based on routing. Next, so what are HA high availability options? I'm going to talk about 3 use cases. One is active standby cluster. Let's say you have one active, one standby sharing the same IP. If failover happens, the standby device is going to send a gap to take ownership of the IP. Then from fabric perspective, it still keeps sending traffic to the same PBR destination, but endpoint location is moved. So it's not PBR failover, but endpoint location change. This is one PBR destination IP, one logical device, 2 concrete devices. The next use case is, imagine if you have 2 firewalls are down, then active standby doesn't help. then you might want to expand more. Then the option is active-active cluster. When it comes to active-active cluster, each firewall vendor slightly have different behavior. So I'm going to talk about firewall behavior in the case of ASA and FTD. So they have firewalls in the same cluster using the same IP. It's one IP and one MAC entry. They are supposed to be connected to the fabric as if it's one logical device. I'm going to double-click this use case in the next slide. The third use case is independent active nodes. So you have multiple HA pairs having multiple PBR destination IPs, and then symmetric PBR going to load balance traffic. I believe the first use case is probably simple and then it's straightforward. So I'm going to double-click the second and the third use case. For active-active cluster, we must connect to the leaf in the same interface. Otherwise, let's say on the left side, you have firewall 1 connected to leaf 3 and 4, and the other one is connected to different leaf, different port channel. Then it's simply flapping. So this is not good, regardless it's ACI or not. So we need to connect firewalls as if it's one logical device. This is one big port channel. Then we are not going to get confused. So this is one important consideration. That said, you can connect firewalls in the different location if it's multi-pod. As long as it's one location per pod, you can distribute the firewalls in different locations. By default, both of the service leaf gonna notify that 10.1.1 is under me. It will cause flapping, but by using any cast service feature, we can get spine has special behavior. Spines are going to prioritize local location because this is close. But they are exchanging information so that even if both of the firewalls in the local port are down, they can start using remote location. That is good for high availability. The third example is independent active nodes. In that case, let's say you can start with one firewall, and then you see slightly number of traffic are increasing. Then traditionally, you might need to replace the small firewall with bigger firewall. But by using symmetric PBR, you can just add additional PBR destinations in the same PBR group. Then by using hash, ACI fabric gonna make sure incoming and return traffic is load balanced to the same firewall. In this illustration, because of the space, I put all of the firewalls in the same service leaf, but the location doesn't matter. You can distribute firewalls across different leaf nodes. It might be better for high availability and resiliency. By default, symmetric PBR hash is based on source destination IP combinations. But if you want, you can change it. For example, if you want same IP, same user, always go to the same PBR destination instead of based on destination IP. Then you can use source IP-based hash for incoming traffic, and then the return traffic, you must check destination IP-based hash because source IP of incoming traffic is equal to destination IP of return traffic. If you use the same value for hash calculation, you can get the same result, which means we can select same firewall. So if you tweak this configuration, please make sure you are getting the same hash result. If we have multiple PBR destinations, what if one of the destinations is down? By default, it's going to be rehashed. So let's say we have 4 types of flows and 4 destinations, nicely load balanced. Let's say the first device is down. Obviously, orange will be impacted. But if you are unlucky, blue that was going through second node is now going through the third node. The third node doesn't know the existing connection. Then existing connection might be impacted. If you don't like it, we can enable resilient hash option. If resilient hash option is enabled, let's say the first node is down, then the orange flow will be redirected to one of the available nodes. At the same time, blue, green, purple, they are going through the original nodes, no impact. But the consideration is that the second node is now getting almost double the amount of traffic. Because the point here is that orange, set of orange flow, is not going to be redistributed across available 3 nodes. We're going to pick up one of the available nodes. Then you might need to set a limit in the steady state. Let's say, thinking about this one failure scenario, you might need to set 50% of usage for each service device, which might not be efficient. Then you have another option, having a backup destination. The backup destination is not going to be used unless primary node is down. If first device is down, the orange flow will be redirected to the backup node. It's going to be additional investment, but comparing to the previous slide, you can potentially use, let's say, 80 or 90% of each device usage in the steady state. So these are typically asked design questions. If you have some other questions, please leave a message in the WebEx team space so that I can understand what you are struggling and I can potentially answer it. The last topic is multi-location data center design. Let me first explain what's the typical design challenge for multi-location data center when it comes to service insertion. It's not specific to ACI or something. I believe this is a general consideration. So let's say you have some site 1, site 2 stretching subnet, and then you have 10.1.1 in site 1, 10.1.1.2 in site 2. Typical mistake we did is putting active standby, independent active standby device as a perimeter firewall. Then, since subnet is stretched, unless you enable host route advertisement, traffic could come to site 1 going to site 2. Then it's most likely the return traffic will choose local exit. Then that firewall doesn't know the incoming traffic, then firewall is supposed to drop traffic. The key point here is it's very important to keep traffic symmetric. So I'm going to explain how we can keep traffic symmetric for multi-pod and multi-site. So let's start with multi-pod. We have 3 options. First option is active standby across pods. Since active device will always take care of traffic, there's no need to think about asymmetric traffic. So it's pretty simple. The second option is active-active cluster across pods. This requires Anycast service feature, and I'm going to double-click this option. The third option is active standby in each pod. This we need symmetric PBR, but this can potentially create unnecessary traffic hairpinning because this is hash-based load balancing. Even if you have source and destination endpoints in port 1, we might choose PBR destination in port 2, and then traffic is coming back. We don't have location awareness that much for east-west, although we can do that for north-south. So we typically recommend the first or second option because multi-pod is one logical fabric, although it's distributed to different locations. So similarly, firewall cluster is kind of one cluster or one HA across pods. So I'm going to cover the second use case because first use case is pretty simple. It should be straightforward. So let me explain how forwarding works for active-active cluster case for both north-south and east-west. For north-south, let's say you have external EPG to web EPG contract, having firewall, 2 firewalls in each pod, and then it's one active-active cluster. For north-south, external EPG to web EPG, we always apply policy on the compute leaf instead of border leaf. And then when redirection happens, because of any cast service feature, 10.1.1 location, we always prefer local location so that we can avoid selecting remote location and then traffic is coming back. So it can optimize traffic path. Of course, if all of the firewalls in the local port are down, you can still use remote location. So this can eliminate unnecessary traffic hairpinning, and also this can provide high availability just in case. Even if traffic is coming in port 1 going to port 2, border leaf doesn't apply policy. We always apply policy on compute leaf. Then the firewall that is in the same pod will be used. For return traffic, the same compute leaf will apply policy because that's how contract works for east, north, south traffic. So this is how we can eliminate traffic hairpinning and also keep traffic symmetric. Then let's take a look at east-west. You have web EPG to app EPG. If it's intra-pod traffic, regardless ingress or egress enforcement, either case, we can just choose local location because they are in the same pod. So there's no unnecessary hairpinning, which is great. And then how about inter-pod traffic? This could cause asymmetric traffic, but thanks to active-active cluster, it will work. So let me explain step by step. Let's say web in port 1 send traffic to app in port 2. Assuming ingress leaf knows the destination already, if that's the case, ingress leaf enforce policy and then choosing the local firewall destination. After that, traffic is going to the destination, which is in port 2. Then the return traffic, if the leaf in port 2 also knows the destination, web endpoint, for some other traffic, then there is a possibility that policy is applied in the ingress leaf in port 2, that's going to choose the local location in port 2. Then asymmetric traffic happens. If it's independent firewall, the firewall in port 2 will drop traffic, but thanks to ASA FTD active-active cluster, they have another link that is called control link, so they know who is the owner of this flow. So by using control link, they're going to forward the traffic going back to the firewall in port 1, who originally saw the incoming traffic. Then traffic is going back to web endpoint nicely. So in summary, by using active-active Cisco ASA FTD cluster, along with any cast service feature with PBR, we can eliminate unnecessary traffic hairpinning. And also thanks to firewall, even if we have asymmetric traffic flow for east-west, this should work. So that's the reason why we kind of recommending active-active cluster across pods. That said, active standby across pod is also fine, because if the location of pods are close enough, probably you don't care about traffic hairpinning that much. How about multi-site? Multi-site, actually first two options, we don't actually recommend it because the intention of multi-site is fault domain isolation. As you can see, each site has a unique independent APIC cluster. So why don't you use same notion for service device? Independent firewalls, active standby or active in the site. So I'm going to double-click this use case, similar to previous example. So let's take a look at north-south traffic for multi-site. Assuming we have service device active standby in each site. But I just use this as an example. You can just use active-active cluster within site or independent active device in site. So imagine you have external EPG to web EPG contract with PBR. Similar to multi-port case, we apply policy on the compute leaf instead of border leaf. Then the local firewall will be chosen. Unlike multi-port, multi-site cannot redirect traffic to the remote location because we expect that we have decent high availability within site. This is one fault domain. If traffic is coming through site 1 going to site 2, policy is applied on compute leaf, then firewall in site 2 is selected. For the return traffic, again, the same compute leaf will apply policy, choosing same firewall so that we can keep traffic symmetric. There's no unnecessary traffic happening. For east or west, EPG web and app, how it would work. For this case, we do provider leaf enforcement. Provider leaf always enforcing a policy that chooses the local firewall for both incoming and return traffic, then we can keep traffic symmetric. That said, you might be wondering, let's say provider endpoint generate traffic. Then provider leaf doesn't know web endpoint yet. Then provider leaf cannot apply policy. To avoid such situation, we must configure consumer EPG subnet for multi-site EPG to EPG PBR. By using subnet as the EPG classification, the provider leaf can always resolve the consumer EPG class ID so that provider leaf can always apply policy. That might be okay if you have network-centric design, let's say one EPG, one bridge domain subnet. But imagine you have multiple EPGs in the same bridge domain subnet, the configuration might be a little bit tedious job. So I'm gonna double click on this consideration in the next section, but before doing this, let me quickly go over how we can ensure the provider leaf enforcement. Because even if consumer leaf can resolve destination class ID, consumer leaf can kind of ignoring policy enforcement. So we introduce special behavior for this. So I'm going to use these class IDs in the zoning rule. So we have 4 zoning rules: consumer to provider, provider to consumer redirect. And then you can see slightly different action. For consumer to provider, we add a special flag that is called redirect override. This is a special flag. So what it does is that if the destination is not a local endpoint, the leaf doesn't apply policy. Policy applied bit is 0, which means egress, provider leaf must apply policy. So we don't need this behavior for return traffic, provider to consumer, because provider leaf should always resolve consumer EPG class ID because of the subnet configuration. But probably nobody loves putting some consumer subnets. And also we didn't support with any PBR in multi-site, but we finally supported it in the beginning of this year by using ACI 604 and NDO 423. So in the last part of my presentation, I'm going to talk about how it works, and I'm going to show you how to configure it. So with any 2 EPG, any 2 specific, we have 2 challenges. One is how to keep traffic symmetric. For that, we use provider leaf enforcement similar to EPG contract with PBR. So we already talked about it. But how we can ensure provider leaf can always resolve the consumer EPG class ID without subnet? For that, we introduce conversational learning. So I'm going to explain that. So let's take a look at with any to app provider redirect contract. Web endpoint in site 1, app endpoint in site 2. So we always apply policy on provider leaf for incoming traffic, and then return traffic, we apply policy on the provider leaf. It's pretty much same with previous example for EPG to EPG. What if the provider leaf doesn't know the consumer endpoint yet? Then we have no choice but to implicitly permit the traffic, which means policy applied bit is set to 0. Then we have new behavior kicks in. The egress leaf in site 1 receiving traffic from site 2 without applying policy. Policy applied bit is 0, and then source step is the overlay unicast step of site 2. So the destination leaf can identify this is from site 2 where firewall 2 was supposed to be inserted, but it's not. So the destination leaf kindly redirect traffic back to firewall in site 2. That is the source site firewall. And then after that, firewall sends traffic back and then going to the destination. So this is how we can recover help in case ingress provider leaf cannot apply policy. That said, you might be wondering, this could cause unnecessary traffic hairpinning that we don't like. But don't worry about this. It's not going to happen continuously, thanks to conversational learning. So we have another new behavior when provider leaf cannot apply policy. So in the previous slide, I mentioned that the destination site 1 egress leaf redirect traffic back. At the same time, the leaf in site 1 generate magical packet, control packet, because 2.1 to 1.1 traffic was not enforced, which means the source leaf didn't know 1.1. So we flip source and destination IP. So the control packet has source IP 1.1, destination IP 2.1, which means traffic is going back to the original source leaf. Then the source provider leaf can receive the traffic. That kicks data plane IP learning. So that after this initial conversational learning, provider leaf can always apply policy on the ingress. So the unnecessary traffic hairpinning could happen only until conversational learning is done. So this is how we can make with any to EPG PBR works without EPG subnet. So this is quite useful because now you don't have to deal with multiple different consumer EPG subnet. So you can do app-centric service insertion in multi-site. The next use case is with any to with any. So this is quite useful if you want to redirect all of the inter-EPG traffic. So let's take a look at with any as a consumer, with any as a provider contract with PBR. So two challenges: how we can keep traffic symmetric, and how we can ensure the ingress leaf node can always resolve destination class ID. So we use conversational learning. It's similar to with any to EPG use case. How about the first challenge? How to keep traffic symmetric? We introduce new behavior. We try to insert both of the firewalls, firewall in source site and firewall in destination site. We redirect traffic to both for both incoming and return traffic if it's inter-site traffic. So don't worry about this. Intra-site traffic, we can still use local firewall. Redirection happens only once. When it comes to inter-site traffic, we redirect traffic twice. Probably it's a little bit hard to imagine what I mean by that. So let me illustrate how forwarding works. So let's say you have VZNE to VZNE contract, PBR. You have web endpoint in site 1, app endpoint in site 2. Web sends traffic to app. Ingress enforcement happens. Traffic is going to firewall 1. And then firewall 1 sends traffic to destination. That's the general behavior. But if it's VZNE, PBR, we have some special new behavior. We redirect traffic again to insert firewall in the destination site as well. The condition is if destination leaf that has VZNE, PBR rule receives the traffic from another site, and if firewall was already inserted in the source site, we redirect the traffic again to insert firewall in the destination site. So you might be wondering how it works. So I will double click that in the next slide. From the local firewall to destination, we don't redirect traffic again because it's intra-site traffic. So let me double click how it works. But the idea is instead of stick on one firewall, we just redirect traffic to both of the firewalls. And then this is applicable only for inter-site traffic. So imagine you have multi-site. Even though you might have inter-site traffic, most of the case, you might prefer to use intra-site traffic within site because that's more efficient. Probably only when it's required or some certain amount of traffic, you might have inter-site traffic. So I don't think inter-site traffic is your majority of traffic. So I think inserting firewall for inserting both of the firewall might not be a big additional resource consumption. So you might be wondering how we can identify if traffic was redirected in the source site. So let me go back to policy applied bit presentation that I showed probably 40 minutes ago. So recap is like 1.1 to 2.1 traffic. If it's enforced by ingress leaf, we have a policy applied bit is set to 1. Then destination leaf can identify if traffic was enforced or not. So this is to indicate policy was applied or not. But we actually have 2 bits to indicate the situation. So we have been using policy applied bit 1, meaning both bits are 1. Then ingress leaf was applied policy, which means egress doesn't have to apply policy. If it's 0, policy was not applied by the ingress leaf, which means egress leaf needs to apply policy. Since we have 2 bits, we can indicate another situation. So we decided to use SP equals 0, DP equals 1 to indicate firewall was already inserted. So this is a new magic, new behavior. So we put this special flag if it's a traffic coming from service EPG going to provider. So let me go back to the previous slide to take a look at traffic workflow. So let's say web to app traffic redirected twice. The first action is just web to app redirect. Traffic is going to firewall 1. After that, traffic from service EPG to app that hits service EPG to VZNE, we put special flag SP equals 0, DP equals 1 to indicate firewall was already inserted in the source site. Then the destination leaf sees the traffic from another site, SP equals 1, DP equals SP equals 0, DP equals 1, which means this is from another site, and firewall was already inserted in source site. Then we need to redirect traffic again After firewall 2 sends traffic back, this will also have a special flag because this is also service EPG to provider. But we don't redirect traffic again because this is intra-site traffic. So the condition is having a special flag, and this is from another site. So that's the reason why we only redirect traffic twice, one in source site, another one in destination site. So this is to ensure for incoming and return traffic, we have both firewalls inserted. So this is a new behavior. Then provider to consumer direction, the return traffic. Let's say ingress in site 2 redirect traffic. Firewall 2 is inserted. From firewall 2, we have a special flag, SP equals 0, DP equals 1. Traffic is going to the destination. And then this is from another site. This is inter-site traffic with special flag. So the destination leaf redirect traffic again to the local PBR destination. So by doing this for both incoming and return traffic, we can ensure both of the firewalls will see both incoming and return traffic. So there is no asymmetric traffic redirection. So you can keep traffic stateful. Again, from local firewall to destination, we don't redirect traffic again because this is intra-site traffic. Hope this makes sense. And then, if ingress leaf doesn't know the destination endpoint yet, we can use the same behavior. So let's say ingress leaf in site 1 doesn't know the destination up endpoint. Traffic is implicitly permitted by ingress leaf in site 1. Traffic is going to the egress leaf in site 2. And then this time, this is inter-site traffic coming from site 1. Policy was not applied. Then we need to respond traffic back, redirect traffic back to the source site, which is site 1. So firewall 1 information is actually available in site 2 because NDO orchestrated that. So destination leaf already know where it's coming from because of VXLAN overlay unicast step. And also, since this is site 1, the destination leaf already know that what's the PBR destination in site 1. So NDO cross-program that important information. So thanks to this, we can redirect traffic back to firewall 1, and then from firewall 1, we have a special flag because this is again from service EPG. Then taking a look at that packet on the destination leaf again, this is a special flag from another site. So redirect happens again, then firewall 2 is inserted. Then from firewall 2 to destination, we don't redirect traffic again because this is intra-site traffic. At the same time, we generate conversational learning packet. In this case, 1.1 to 2.1 is the original traffic that was not enforced. Then we need to get ingress leaf LAN 2.1. Then the control magical packet, source IP is 2.1, destination IP is 1.1. Then ingress leaf in site 1 can learn where 2.1 and what is the class ID of 2.1. So unnecessary traffic hairpinning happens just until conversational learning is done. So this is how BZNE works. It seems very complicated, but usually you don't have to care about it. But I just want to let you know that what's actually happening behind the scene. So once you have BZNE contract with PBR, all of the inter-EPG communication will be redirected. You can specify specific port, let's say TCP redirect, then all of the TCP inter-EPG communication will be redirected. That said, you might want to bypass firewall if it's not required, because if you redirect traffic, everything, firewall gonna be exhausted. So we have an option to bypass firewall. So I'm going to show you two examples. The first example is intra-EPG traffic. Actually, you don't need to add additional configuration for this, because by default, we have intra-EPG permit rule. That is implicit. It's not in zoning rule, but it exists with priority 3 that wins over priority 17 for with any. So even without any configuration, unless you have intra-EPG isolation or intra-EPG contract, intra-EPG traffic is just permitted. If destination class ID is unknown in the ingress, policy applied bit is 0, and then destination leaf applies policy. If ingress leaf can resolve destination class ID, ingress leaf applies policy, and then egress doesn't do anything, just forward traffic. So this is intra-EPG traffic. So even though you have with any PBR, intra-EPG traffic is not going through firewall. Then you might want to exclude some EPG to EPG communication. You can bypass firewall by configuring permit contract. So you don't need to deal with PBR service graph configuration again, because it's just a one contract permit rule. You can put multiple consumers and multiple provider EPGs to create some bypass list. Because EPG to EPG, specific to specific, wins over with any to with any. That's what we already covered in the beginning part of the presentation. So by configuring web to app contract permit, if ingress leaf can resolve destination class ID, the traffic is just permitted. If not, egress leaf will apply policy. So you can potentially start with any to any PBR to redirect traffic. And then once you identify what traffic are going through, maybe you can slightly excluding some specific traffic, because usually we don't know what traffic to be denied, permitted, or redirected. So maybe you can start with permit IP redirect all, and then excluding, let's say, SSH, we don't need to redirect to firewall, or some specific encrypted packet, you don't need to redirect to firewall. So you can keep adding more specific rule to excluding firewall redirection. So hope this can simplify your use case and expanding the multi-site service insertion use case. So I don't have a time to cover other use cases newly supported in NDO 423 and ACI 604. But in addition to VZNE to VZNE, VZNE to EPG, we support VZNE to external EPG and external EPG to external EPG transit case. Except VZNE to EPG, we redirect traffic in both sites if it's inter-site traffic. And then we support one node, one arm. And then only L3 out to L3 out, we support inter-VRF as well. No need to configure EPG subnet anymore, except L3 out, because L3 out subnet, we always need to put subnet. But for regular EPGs, you don't need to put subnet. If you want to bypass it, you can just create a specific to specific permit. You still need firewall in each site. This is also a common requirement or feedback from customer that I want to put firewall in just one of the sites. That's currently not available. So if you have any feedback or requirement, please come to us. Maybe we can work on that next. So ESG is also commonly asked question. So unfortunately, ESG is not supported in multi-site, but it's in the roadmap. This is the last topic today. We introduced a new configuration workflow on NDO for L4-L7. The reason is that, to be honest, many people think service graph configuration, especially PBR, is complicated. So we try to simplify configuration as much as possible. So after I explaining what is the APIC configuration and then explaining what is the new configuration, I'm going to show you the demo. So let me recap how current ACI PBR configuration looks like for service graph. For service graph, we need a contract because that's another contract action. Contract is mandatory. Then we need to create a service graph template to define firewall or firewall plus load balancer or load balancer only. And then we attach that service graph to the contract. So these two components are mandatory. In addition to this, we need to define what sort of device are connected to where in the fabric. If it's physical domain, you need to select leaf, port, VLAN, and then if it's virtual appliance, you need to specify VMM domain, and then let EPIC allocate dynamic VLAN. Then you need to define device selection policy, because depending on configuration combination, let's say you have 4 firewalls. Which firewall we need to use? So we need to let EPIC know when we need to use which device. So it's based on contract name, graph name, and node name in the service graph. We need to select bridge domain, where this firewall interface is located, and so on. So we have quite a few objects, and we need to understand how to build the blocks. So unfortunately, this is what it is, because we need to let EPIC know when we need to use which device and where to place this interface. In addition to this, if it's PBR, we need to add more configuration. Because of PBR destination definition, we need to configure what's the destination IP and the MAC. And also we have hash options such as source IP, destination IP. Although it's not mandatory configuration, you can just use default configuration. But we have multiple different options because we are enhancing this feature, resilient hash and so on. And then we have tracking option, IPSLA. It's not mandatory, but it's most likely the case that you're going to enable this because it's better to detect failure. So you need to select the protocol and the interval and so on. And then we need to create a health group. So you see how complex it is, but we have multiple objects you need to build. Then when it comes to multi-site, we've been supporting multi-site PBR since ACI 3.2, but we need to configure EPIC locally and also LDO. So we have 2 separate locations. Firstly, EPIC admin in each site, they need to create L4-L7 device, PBR policy, and IPSLA tracking policy. The original intention that we had is that each site might have a different physical connectivity and so on. It might make sense to let local EPIC admin configure where it's connected. And then on the LDO admin, they're going to take care of policy, contract, EPG stretch, and so on. So LDO admin is going to create a service graph template attaching to the contract. And then as part of this, LDO is going to ask which BD we want to use, and then which device that is already defined on EPIC should be used. So these 2 separate configuration locations. And the object model-wise, it's pretty much the replication of what we've been doing on EPIC. We tried to simplify this, and it was OK, but it was not as simple as we wished. So in the new configuration, you don't need to touch EPIC. We can do everything from LDO. So we have just 3 steps. And actually, one of them is optional. But as I mentioned, it's most likely, it's better to configure IPSLA tracking so that you can detect failure faster. First step is creating IPSLA policy. You need to specify ICMP, TCP, or interval. This is not something we can ignore. We must configure it. And then the second step, we just define service device template so we can consolidate independent objects that we have been dealing with to one object, service device template. And then the third step is just inserting and selecting which service device you want to insert to which contract. So we just have 3 steps. So in the last part of this session, I'm going to show you how new VZNE PBR configuration works. So I have a video recording here. So this is NDO UI. I'm not sure how familiar you are regarding multi-site, but in multi-site, we have a template called tenant template, where we define tenant. Inside of application template, we have VRF, bridge domain, EPGs, and the contract. So basically, application template is a mandatory component. And then you can see L3 out, monitoring policy, service device, and the tenant policies. So today, we are going to use application policy because this is mandatory to define EPG. In addition to this, we use service device policy because we are going to define service device. And then tenant policies, this is where we are going to configure IPSLA policy. So we are going to touch application template, service device, and the tenant policies. And I already have some application template configured, VRF, bridge domain, EPGs. And I have 2 sites, site 1 and site 2. And I already configure firewall in each site. So let me play this recording. Okay. And then I'm going to share the video on WebEx TeamSpace after this session. It's quite big, but if you want to see the video in a little bit better resolution, please join WebEx Space. I'm going to post it later, this presentation. So I just played it. I already have application template where I already configure VRF, EPGs, and so on. And it's already pushed to both site 1 and site 2. I have a couple of EPGs, 1 VRF, couple of bridge domains, and filter. And I have web endpoint in site 1, 10.1.11, and app endpoint in site 2, 10.1.2.22. So I'm going to generate a ping from web to app. That is failed because I haven't configured the contract yet. So let me create a VZNE to VZNE contract to just permit traffic at this moment. So creating VZNE to VZNE contract, and then associating this to VZNE. So VZNE at the VRF, associating contract, consumer, and also the provider. So this is just a VZNE to VZNE permit contract in this VRF. So deploying this template to both sites, and it's going to immediately permit traffic. On the right top side, you see the ping is going on. So this is pretty useful. It's going to just permit everything in the VRF. And then going to tenant policy, where I'm going to define IPSLA policy. I'm going to create object IPSLA monitoring policy on the bottom, and I just call it ICMP 3 second, and then frequency is 3 seconds. Once create 10 policies, I'm going to associate this to both sites. We need both sites having this IPSLA policy. So deploying this, it's going to just create IPSLA policy on both sides. And then the important part is service device template. So in this template, I associate the same tenants called the service chaining. And the initial step is create service device cluster. Here, it's going to ask you what sort of device I want to use. Firewall, 1 arm, and then we have 2 arm and advanced use case, but I'm going to just create 1 arm. I just stop here. So if you select 2 arm, it's going to ask you selecting 2 bridge domains because it's 2 arm. But since I just select 1 arm, it's going to just ask me 1 bridge domain. And then the last selection is whether I want to enable redirect on this interface or not. Then it's going to ask whether I want to enable IPSL policy or not. And the advanced setting, it's hidden by default because most of the case people wouldn't use it, so we hide this by default. And the next step is associating this to both sides. Then it's going to ask you where it's connected. So I'm going to use virtual appliances, so I'm just going to select VMM domain in site 1, and it's going to dynamically allocate VLAN, so I don't need to put VLAN. But I still need to specify what's the VM. So I have 2 firewalls in each site. Site 1 firewall 1 as an active device, and I'm adding the second firewall in site 1. And then selecting virtual NIC, because APIC is going to automatically change the port group setting. And then PBR destination IP for site 1. This is one IP because this is active standby cluster. Then I'm going to do the same for site 2, selecting site 2 VMM domain. VLAN can be empty, enhanced log, selecting VM name. I have active standby pair in site 2 as well. So I'm going to select one VM, one VNIC, and then second VM, and one NIC. If you selected 2ARM, you need to do this for second interface as well. But NDO going to nicely ask you, what is the mandatory configuration for you? So 11.2 is the IP for site 2. Then I'm going to deploy this, but at this moment, there is no contract update. I'm just going to create L4-L7 device. Nothing is changed, no traffic impact. I just define device. The next step and the last step is associating this to contract. But before doing this, I need to tweak 2 new options for VZNE PBR. Because we have conversational learning behavior and new redirect back to site 2, site 1 behavior. So we need to click L3 multicast for conversational learning and site-aware policy enforcement for new redirection behavior. Then going to down service chaining section as the contract, we can see VZNE as a consumer and provider, and then selecting service device, and then redirection is enabled on both. Since it's one ARM, it's automatically populated. I don't have to select the interface. So by deploying this, it's going to associate the service graph template to the contract. And then once programming is done, zoning rule programming is done, the traffic is immediately started to be redirected by Fabric. So let me check APIC configuration is updated. So VZNE graph is rendered on both site 1 and site 2. And then checking the VM configuration for firewall, the port group configuration is updated by APIC so that this virtual machine is ready to receiving traffic. So let's take a look at if firewall actually receiving a traffic. This is the active firewall in site 1. So I just enable screen capture, and then I keep ping going on. So I see the traffic between web and app inter-site in both firewall because it's inter-site traffic. Firewall in both sites should receive the traffic. And if I check web client, still keep pinging to app. And if I want to remove this firewall, I just need to remove service chaining from the contract and then redeploy it, and then immediately contract is going back to permit. As you can see, configuration is removed on site 1 and site 2. And then when checking the firewall VM, the port group configuration is also automatically updated. So that's it. I hope this is simple enough. And with that, conclusion of this presentation. So we covered how ACI PBR works, use cases, and design options. In a nutshell, this is very flexible. You can redirect traffic based on contract. We can even do intra-subnet any-to-any contract. And we can scale easily symmetric PBR, combining L1, L2, L3 PBR, And we can even do multi-location data center by using VZNE PBR, and we can simplify configuration by using a new workflow available on NDO. Unfortunately, I cannot cover other details, but if you want to know more, please take a look at ACI PBR white paper. With that, I conclude my session. Please complete your survey. Please let us know what you want to hear next. Continue your education. So if you want to know more detail about the PBR, we have a TAC troubleshooting session, 4 p.m. today. If you have any question, please join WebEx space. And with that, thank you for joining my session. I hope you enjoy the rest of your Cisco Live. Thank you.